ALA. So let's see. Yeah. Here's where we are. You probably already know you're going to log in with the name 2222 over here. So there's our link. Oh, that's not our link. That's our link. Two, 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 two. Now put us all on the same page, literally. You're already there. So yeah, just go ahead and work on this. I think if you have seen logarithms, you're going to be able to between the two of you, you'll be able to do a lot with this. Here's the definition of the logarithm. What is the logarithm? It's an exponent. The exponent, the power to which you raise the base in order to get the argument of the logarithm. And if you want clear, I mean that's a clear statement, but here's a slide that looks good for definition of a logarithm. Okay. This logarithmic equation, y equals log base b of x, that's just the same thing as the familiar b to the y equals x, an exponential equation, where of course y, which is the logarithm, is the exponent. So use the text tool or pen tool. Yeah, with exponents, I mean, you could do it with the caret if you wanted to use the text tool. The caret, which is the thing above the 6 on your keyboard. And I'll keep an eye on the chat, Andrea, because it seems that you might not, well, I don't know, even on mobile, you should be able to talk so we can hear you. In exponential and logarithmic equations, the base is the base. Base of the exponential in the exponential equation is the same as the base in the logarithmic equation.
Sir, is B correct?
Well, that is the same thing as the question. Okay, so what you've given is the logarithmic form. So now you'll convert it to the exponential form. Yep. So Andrea, you know that's ln for part B there on the bottom. That's ln h. But what you've written is correct. You didn't do anything wrong. I was just saying that part B down here on the bottom is the same thing as ln h equals k. Same thing.
So E and L and N can switch, are versatile?
Log base e, that's the same thing as ln, right? The natural,
Oh, okay.
yeah. Where e, of course, is the number. Um, e is the number, which is approximately 2.72. But then we have this matter of the common logarithm. Part C at the top on side 2. There we go. You don't have to do all that. It's okay though. I mean, you
But for
can,
this problem, would there be imaginary numbers for this problem?
for B, no, no, they're real.
Oh, okay. Because I did get one real and then I did get like an imaginary.
Oh, okay. Oh, so you went to your calculator and got cube root of 8. Is that right? I mean, there are two non-real roots of 8.
Yeah, that's what I got. That's what I thought it was.
Um, okay, how did you get that?
Since I thought that A goes into A can be separated three times, so and then I put the square root of three. Oh, I have no idea. But I and then I got x equals 2 also.
Yeah, I think they're just looking for 2. Um, I believe we're going on, we want a real base of the logarithm. Um, so let's see what was advertised over here. Yeah, I mean, they're saying be positive. So yeah, we're going with just the real root there because the base they're saying is positive. We didn't talk about the fine print for the definition of the logarithm, but B, the base is positive. The argument is also positive. The base is not equal to 1 for the same reason that we don't want the base of an exponential equation or an exponential function to be 1. So base
Oh, okay.
and argument positive for the definition of logarithmic function. kind of interesting though. The non-real roots of 8. Okay, so base is a 10, right? For the common logarithm, the base is 10. Isn't that what you put back here, Jacqueline? Yeah, on part C there.
Oh yeah, yes, no, I did write it wrong in my notes.
Okay, you can check them too, right? I mean, if you want to check that answer, you could say, well, let's see, log x equals 4, log 10,000, and it's 4. So yeah. So Andrea, you might have seen on part A, you might have seen the negative and thought you didn't want any part of that. But remember, I'm on this big don't simplify anything kick. That works. Part A, you can do that without having to even have any idea what a negative exponent means. Yeah. All right. And put it in a decimal. That works. It's 1/8, which is 0.125. So to do those, we had to understand common log and natural log. Common log is the one with base 10, and natural log is the one with base E.
Sir, I was a bit confused with these. So how would you start that? Would you first simplify the parentheses first, or would you,
Oh, I'm on which one?
or on the use the definition of common and natural
Oh,
logarithm to simplify? Yeah, the A.
okay. So, well, try this. Let's call this whole expression y. Let's call it y. And then figure out the value of y kind of in a similar way to what you've been doing.
Oh, so would it be that you would try to set up, so then it'd be 10y equals 10 to the power of 3?
10 to the y equals 10 to the 3.
Oh, okay. All right then. Thank you. No, that makes more
Okay.
sense.
Yes. Okay, so um, yes, that's what I was going to say. What is log 100 to the 7th? It's 14. That's what it is. Make a comment about this problem here. When you say log base 10, 10 to the 3rd, it has the form log base a to the x. And so that's why we have a property that says log base a to the x just equals x. Because what's happening is the logarithm and the exponential, which are inverse operations, they undo each other. They cancel each other. And so you just get the x. And while you all work on part C, D, E, and then B down below, I'm going to look for a good statement of those properties that I was just talking about. There it is. So if you look back in the Zoom, I was just talking about this property here, right? Because you've got the log and the exponential canceling. Well, they could cancel this way too. B to the is the inverse of log base B of. and you can get the x out of that too. And this is also useful for solving logarithmic and exponential equations.
Sir, I have a question. I'm kind of stuck on number D, and I'm wondering, so if the exponent is the same thing as the parentheses in B, or would I have to solve that a bit differently? Because
Um,
if I did that right there, then wouldn't it end up as a decimal?
okay, well, um, you've got two e's in there. Um, you've got the base e, and you've got an e in the argument.
Oh, okay.
I mean, what you could do is, I mean, you could call it all y again, and then figure out what y is. That's another option. Okay, not quite. We have log base e of e to the negative 6.7, and all of that equals y. So what's the equivalent exponential equation? How's it going, Jacqueline? Is that making sense? That approach?
I'm still a bit confused there, but I'm trying to figure that out.
Let's say this. Part D is formally the same thing as part A. In fact, part D, you can just use this rule to do. It's the same thing as A with different numbers. Got it.
Yeah, I was just a bit confused about the exponents.
Yeah, sure. Okay, so there's a rule like the one boxed in purple that just makes sense like that one does. And it goes like this. Oh, there it is. Okay, so the one boxed in purple that we used for part A and part D was one of these, which says, okay, the log and the exponential, they're inverses, so you can cancel. Now, what we have is that's also true here. Cancel, and you just have the x. So I believe it's 10 raised to the log base 10 of, is it 37?
It was negative 6.7, I believe.
Oh, I'm part C. I,
Oh, yeah, 37. Sorry. I thought you were talking about the.
oh no, I'm talking about C and E because they're both the same as far as kind of the rule that you're using. So in C, you have 10 raised to the log. Of course, we know that's base 10. Sneak that in there. 37, and then go to hacking on that. The exponential with base 10 cancels the log with base 10, and you just come out with the 37. And so 37 is actually just the answer to part D. I'm sorry, C. I'm sorry. 37 is the answer to C. Right? Think of it this way. Um, right, for part E. think of it
Yeah,
this way.
the ln would have a base of e, so then they cancel out the e with the e, and then it'd just be 4.
Right, right, right. Like log, yeah. I was going to say, and this is, I guess, more for people on recording, log 37, the power that you have to raise 10 to get 37. Don't know what it is exactly. I know it's 1 point something, log 37. 1 point something. And then what if we took that number and we said, okay, what's 10 raised to that number? 10 raised to 1.56820 2017. That was a good year for the Astros, unlike this year. Oh, it's 37. So basically, the exponential and the logarithmic undid each other. So, Andrea, why don't you go ahead and put the answer there, at least the answer for part C on slide 4. Okay. So that said, use the definition of common and natural logarithm to get those values. So, Andrea, for part A, if we call it y, how do we solve, how do we get how do we get the value of y? We call all that y. think she's on her phone. Fantastic. Square root of 7. Square root of 7. 2.645751311. What a perfectly weird, lifeless number. What if we try to hack on this? Let's see. 7 raised to the x, and we're looking for the value of that thing to be 2.64575 for 7 to the x. We're going to have that familiar exponential type graph from section 6.2, is it? And we want to know when that's 2.64575. Let's see. Now, if we just use trace, I think it's too crude to give us what we want here. 2.42, 3.25. Yeah, that doesn't work. So, well, we'll zoom in. What we're doing here is we're inductively discovering a rule of exponents that's needed in this problem. See, do we have enough window to get that? No. So let's put the top of the window at 2.9. And try the old trace key, which these youngsters have never used. That's like old school TI 81 key to use. Okay, we're getting close. Look at that value of X. Interesting. Let's see. Um, Zoom in. Trace. Anyway, it's a half. Okay, and the reason is that the square root is the 1/2 power. So we're finding log base 7 of 7 to the 1/2, which is hack 1/2. Okay. So the rule of exponents that we, need to own here is that the nth root of a is the 1/nth power of a. So that's a rule of exponents. Part D,
Oh, okay, that makes sense. Thank you.
you're welcome. Part D is also going to involve a rule of exponents, which might not be known. Do you hear the ice cream truck? Now you might be able to figure out D because if you watch the videos, we did the pre-class work on 6.4, then you might have, I can't remember exactly, but you might have seen the video on the natural logarithmic function. Its graph is going to be like the graph of any log base b of x function. And here, let's zoom in. In part D here, we have x is equal to 1. Jay, what is the equivalent exponential equation to ln1 equals y?
E to the power of y equals 1.
Yes. So what is the power that you have to raise the number e to get 1? What is the power that you have to raise 2.721828 da 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 to get 1? Well, it's not going to be as much as 1 because e to the 1 is equal to e, which is too big of a number. In fact, let's look at e to the x. It equals Second ln is e to the x. So looking at the inverse, that didn't register. So let's look at the exponential function.
Or would it be 0 because anything to the power of 0 will equal 1?
That's right. So someone write it up. So what are y'all using for a calculator? Are you using like today, like right now? Of course, on a test, you would never think of using an online calculator. Um, you only use a handheld calculator.
I have a T183, sir.
Okay. All right. So anyway, I guess I'll just do the sharing here. Um, let's think about the natural log and the common log. Of course, we just looked at this. So let's see. In fact, let's do something different. Let's do, instead of A and B, let's do C, D, and E. Let's look at C, D, and E. Log base 2 of X. Now, question is, how do you, even put that in the calculator? Now, the calculator does allow um, you to, put a different base if you know where to find it in the menus. Oh, okay. Okay. Oh, you're all right. So what we'd have to do for a problem like C is use change of base and call that log X over log 2. Unless we knew where to find the different base in the TI graphing calculator. Which, if you know where that is, that's not a problem. But that's the same thing, according to what we call the change of base formula. In the calculator, where that is, just base 2, because on the face of it, all we see is base 10 and base E. That's all we see. So to get base 2, we have to go math and then scroll to log base, and then we can put base 2. Now we still have to be able to use change of base formula even if we do this. All right, and then we'll look at log base 5 of x. Log, oh yeah, we need the log base thing. Math, scroll up or down to a, base is 5x, and then 25. Math, a is log base 25. So which one do we think? Okay, well, first we'll get the log base 2. Now, in a way, these all look the same. So, but what we can determine is which one comes in above or below the other. So the more, the larger the base we have, the more the thing comes in underneath for values of x greater than 1. Okay, so over here on the right, it's going to be the inverse order of what we see. So now, thing is, it didn't actually go in a row for our choices because 10 and E don't fit in, in order with the 2, 5, and 25. So in order, they would be 2, and then E would be the second one, and that's f of x.
Then it'd be D, then it'd be A, and then it'd be E.
Yeah, so it's base 2, 2.72, 5, 10, and then 25 in order. Smallest to tallest. Reverse that to know how to match those up with these curves as we see them lettered over on the right. And it's kind of confusing. They use big letters and little letters. But 2 is going to be the lesser one. The 2 is the highest one, actually. 2 is the highest one. So A, and then B, and then C, and then D, and then E. That problem needs some work. I love these activities, but that problem, I know the people that created this. They're from Santa Ana College, where I used to teach a long time ago. But that one needs some work. All right. Well, let's see. I think it's about 5:30. So that'll get it done for today. If I may just, peek at the rest of this, and then we'll call it a day. Just give me 1 minute. X and Y intercepts if they exist. It's good to memorize these graphs, I'll say that. Okay, that'll get it done. Have an awesome rest of the day.
Have a good day too, sir. Thank you.
Thank you. Appreciate your contributions.